Okay, so we want to do an example of a one sample t-test. We're going to talk about means. We have this pretty quick little snippet for a problem here. It says you have a company that's developing a battery, and they want to develop this battery that lasts over 5 hours, so over 300 minutes. All right, and they have a test of 12 of them, and they wrote down how long they lasted. All right, so for the first part, what do I have to do? Very good, right? So Lily, you'll notice that this is not different yet. Still have to define the parameter. All right, now remember, the statement we used to say was let P represent whatever. Now we're going to say let mu. Let mu. Mu is our population mean, which we don't know. All right, so we're going to say let mu represent the average lifespan of all batteries. All right, you can put made by this company. Right, ultimately I just care about batteries that this company makes. So something like that. Let mu represent the average lifespan of all the batteries. Okay? Now after that, we're going to do our hypotheses. What am I going to use for the null hypothesis? No, not for the null, right? And remember, think back to yesterday when we went over the test. Always should be equals. But am I going to be using P equals? No, I'm using mu. Right? This is a good thing to link in your brain. So whatever you define up here for the parameter should be in your hypotheses. Always the same. All right, so what do I think right now is happening at this company? What's the average lifespan of batteries that we think is happening right now? 5 hours. I'm going to write it in minutes, Ureth. You could put 5 hours. I totally accept it. But because they gave me the data in minutes, I'm going to go ahead and write 300 minutes. But I would accept 5 hours.
Would you have to put in minutes?
No, you don't. I just want to make it clear that because we is it hours or minutes, I want to make sure you know I'm talking about minutes. All right, what about the alternative then? Now, I think, Jarvis, you were onto this with the null. How do you know it's greater than? Because you said greater than. Okay, be careful when you look at the data values, right? Because in theory, Jarvis, if this is your job, right, you don't know the data values yet. You should be doing this part before you actually test it. So, but it's a good thing to do for like the course, but not necessarily for out if you're doing this for your job. So good thought. But it says in the problem that they are setting a goal that lasts over 5 hours. So they're hoping to prove that these batteries are going to last over or above 300 minutes. Okay, are there any questions about the parameter or the hypotheses? I know it's different, but I hope you are seeing that there are a lot of similarities here. Right, the process is the same. Passing notes. Gosh, you guys are so cute. Okay. Busted, right? Caught. Okay. Let's do the model. All right? I'm going to do this, even though, I hate doing this. I love playing the teacher card of not doing it, but I will do it today. I'm feeling good. So here we go. The independence assumption. Who's got it? At the start, I heard somebody. Who's got it? Perfect. Well done, Kiara. One battery's lifespan will not affect another's. So one battery's lifespan will not affect others. Do you need something, Jarvis? Like, do you need to do jumping jacks, run around? I don't have a 5-hour energy, so I'm sorry, I cannot give it to you. They don't? Really? It's poison? Oh my gosh. How is it still on the market? You almost died driving with it? This is getting really intense. I did at one point when I was 18 have 2 Red Bulls back to back, and I thought my heart was going to explode. But I made it. Those were scary. Those were intense. Definitely felt like I had wings. Okay. The next condition is going to be the randomization condition. I'm just going to power through.
These 12 batteries are a good representation
Of all the batteries, because your ref noticed, does it say anything about random sample? It doesn't. So your ref has in her hip pocket, she's got that statement that these 12 batteries are a good representation of all the batteries. So these 12 batteries are a good representation of all batteries. Okay, and what about the 10% condition? So times 10, and so how many batteries do we need this company to be producing? Over, I'm not sure why we're saying 1,200, because 12 times 10 is 120, right? I mean, I'm sure they're producing over 1,200, right? But really, we only need them to be producing over 120. So as long as, I'm going to call them Batco, produces over 120 batteries. What happened there? Batteries. Our sample size is not too but large. Yes.
I always use it 12 and 2% of all batteries.
Yes, you can also use that. All right. So Leslie said that she uses the sample size of 12 is less than 10% of all batteries made. Totally fine. Whatever way you want to do it, that's fine with me. I'll accept both. Okay, so again, back to what we just said earlier. Is that really any different? No, that's the same, but here's where it gets different. Okay? So instead of doing a sample size assumption like we did with proportions, now we have the normal population assumption. I know. I understand it's not the most exciting material. I like it. I think it's exciting, but it can get a little boring.
I'm excited.
Cool. Now, Saul, if you're excited, what statement am I going to write about this normal population assumption?
It's large enough.
No, see, you're thinking proportions. What am I saying, Jarvis? Yes, so I need to write in my statement that I think the distribution of all batteries is unimodal and symmetric. Or, in other words, normal. And I know that sounds redundant because we're saying the normal population assumption, and then I'm basically saying I think it's normal, right? But I have to put it in context, right? The batteries. Now, I don't know if that's true because they did not give me all of the battery lifespans for all the batteries they produce. So I have to check the nearly normal condition, which Jarvis is correct, is histogram. Now, I've already made the histogram, all right? And if I'm giving this to you on a quiz or a test, I will provide for you the histogram, okay? But we've gone over how to make histograms in Desmos, so in theory you could do it, and you'll notice that's where I made my histogram.
So would we draw it out?
Exactly, you would need to sketch it. Just a quick, like a rough sketch, right? Nothing, like, don't take more than 1 minute to sketch it. What do you guys think? Do you think this looks unimodal and roughly symmetric for this sample? Right? Remember, this is just those 12 battery lifespans. And I think it does. Now, what if it shows skewness? Okay, well then what would I write? Okay, what if it showed an outlier? What if it showed something other than this, is what I'm asking.
It's not normal. It's not
Okay, but you need to mention something. You need to mention that I'm worried, right? Because if it doesn't, look unimodal and roughly symmetric, then I'm worried that I shouldn't be doing this. What makes me less worried? What makes me less worried? More data values, right? A larger sample size. So if this had shown skewness or outliers or gaps or multiple humps, then I'm not worried if my sample size is 250 batteries. That's a very large sample. But 12 batteries, that's a tiny sample. So I'd be really worried if this wasn't unimodal and roughly symmetric. Okay? Do you guys sketch it? Everybody sketch it? Excellent. Fine. Now, once Edgar's done sketching, I'm ready to do what?
The mechanics.
But even before that, you're right, you're right, but there's one thing I gotta say. No, I don't have to do anything. There you go, right? So I'm trying to show you it's the same kind of stuff, right? We're not changing really that much. It's right. It's the same kind of thing, just a little different, right? That's what I want you to tell yourself. It's kind of the same thing, just a little different, to make you feel a little bit more confident in doing this. All right? So I'm going to write that statement now. Edgar, you good? Okay. Did you check yes or no? Anyone? Yeah, you guys caught that reference? George Strait? Check. Yeah. Yes, I love it. I don't know what the question is, but just, the goat, the king. All right. What were we doing? Stats. Okay, so the conditions have been... You broke your wrist, and that's how much it hurts? Man, the conditions have been satisfied. Now be careful here. So I will use a T distribution model with, and this is going to be interesting, you've never done this before, with 11 degrees of freedom. You'll probably wonder how I got that number, but figure it out pretty quickly. To run a one sample t-test. Woo! I feel like that always takes longer for me than the actual mechanics. Like when I actually do it, it's like I actually did that. I think that always takes longer than the actual math part. Okay, do you guys see how I got 11 degrees of freedom? The 12 is a sample size. You subtract 1. All right? So do sample size minus 1. N minus 1 for degrees of freedom. N minus 1 for degrees of freedom. And that was in that equation. You got it. But I want to see it in the statement, right? Because remember, if I just say I'm using a T distribution model and I don't describe what the degrees of freedom is, then I don't know actually what model I'm using. Because remember, normal model is always the same. T models are different depending on the degrees of freedom. Changes their shape. Yes, you do the sample size of 12 batteries and subtract 1. For a one sample t-test, it's always n minus 1. Now you'll see next week when we get into 2 sample t-tests, it's not n minus 2. Most people think that, but it's not. You'll see. We're going to let the technology tell us what it is. Okay. All right. Let's do the math. Okay. Let's write down stuff that we know right now. We know the sample size is 12. We know the degrees of freedom is 11. Do we know Y bar?
No.
We don't know the sample mean yet. We're going to find it. Do we know S, the sample standard deviation? No, we don't know that yet. Enter the yellow calculator. Everyone have one? No. Of course. I'll get one back here. You got one? You need one, Saul? You got one? Okay. All right. So what I want you to do is I want you to hit data. Or data. Hit data. And we're going to type in those 12 numbers. I'll put them back on the screen for you. So 321. Enter. 295, enter. 332, enter. 351, enter. 281, enter. 336, enter. 311, enter. 253, enter. 270, enter. 326, enter. 311, enter. 288, enter. All right, I got my 12. That's been a long time since you've done this. Let's see if you remember. So what did you say? Okay, that sounds like a personal problem. No, you don't have to put anything in list 2. Good question, Red. We're not doing any type of frequency. It's just all these numbers are one time. So what you're going to do is you're going to hit second data. Second data is statistics. We're going to do one variable statistics. Number 1. I'm going to wait because some people are still typing in. You got it, Leslie? So you hit second data and one variable stats is number 1. We have all of our data in list 1. That's where I put it. So enter. Frequency, right? Frequency, we're saying these are only happening one time. So leave it on 1. Hit enter, calculate, and let's write down our Y bar is 306.25. X bar. I write Y bar. It's the one with the bar. You find it? Good question. So in the calculator it uses X bar. The reason I use Y bar is because if you guys go into advanced statistics in college, you're going to be doing linear regression with multiple variables. So you're going to be using like Y sub 1, Y sub 2, Y sub 3, Y sub 4. So I want to get you used to using Y. It doesn't matter, right? If you want to use X, cool with it. All right, what's our standard deviation? Do you remember which one to pick? It's SX. SX, so number 3, SX. 29.31. You okay? Okay. Well, if you cleared it, yeah, you've gotten 0. All right, so here are the numbers we need to figure out our T critical value. Gosh, that was fun to say, right? No more Z's. So I'm going to write T sub 11. Why did I put that subscript 11? Degrees of freedom. Very good. Equals Y bar minus mu over the standard error of Y bar. Equals. So my Y bar is 306.25 minus. Do you remember what my mu is? What do I think right now is the best idea for the average lifespan? 300 minutes. Very good. Always go back to your null hypothesis. Divided by, all right, and this formula is not the square root of PQ over N like we've done before. This is S over the square root of N. So it's going to be 29.31 over the square root of 12. You got it, Jarvis. All right. Now, it would not be a day that ends in Y if we didn't use Math Cracker. Yes, I'm still waiting on that email. What's this? Oh, whatever. Okay. So, I sent you this link. Don't feel like you need to go through it right now with me. It's okay. All right, I just want to find my T. That was your fault. That was all your fault. Did you just say only you can prevent forest fires? That was pretty good. Okay. Oh, yeah, you could. But I want to show you you're going to get the p-value here. All right. Oh, the p-value. We kind of need that. All right, there we go. So, always for null, we're using equals, right? Always for null is equals. What was our alternative symbol? Greater than. Very good. All right. What is our mu? 300. Come on. Come on. 300. 300. Excellent. What does our sample mean? So that's our Y bar. Okay. What about our sample standard deviation? So S. Excellent. And our sample size? 12. And what did you guys want to use for the alpha? What he said? Uh-oh. Come on. You can do it. All right, let's try it again. Wait for it. Not giving you hope yet. Tab. Yes. 105. Can I get to solve, though? That's the question. Oh, I went by it. Where is it? There it is. Solve. Are you okay? SOHCAHTOA. Got one giggle. Worth it. Do you guys miss trig? Do you ever miss trigonometry? I think it worked. Did it work? You miss what? Yes. No, I don't know if it works. Oh, it worked. Yes. Okay. Here we go. So you can see this is what we just did on our paper. On your paper, you wrote this. So our T critical value, so instead of our Z score, it's a T score of 0.739. So 0.739. Now, I gave you guys a whole new slide. So below this is a fresh slide. If you want to draw that curve. And watch. You got to make sure you watch, right? This one is a T model. Do you guys see it? Right? Do you see my T model? Thank you, right? You can see it's subtle, but you could see the difference. There's no difference. I mean, there is, right? It is different. I'll show you in a computer how it's different. But like when you sketch it, don't worry about making it different. Just do it like the normal. Okay, so what was it, 739? Yes. So that's going to be somewhere over here. And we're shading to the right. Now, Math Cracker is telling me that my p-value is 0.238. Because the alternative hypothesis was greater than. Right here. So greater. If that had been less than, we'd be shading to the left. If it's not equal to, then we shade both tails. Okay, so who's got our conclusion for this p-value of 0.238? And remember, we're using an alpha of 0.05. Who's got it? Nobody has. Why?
Because the p-value is below our alpha.
Close, almost. You were so close. It's above, right? Our p-value is above alpha, so we do not have enough evidence to reject the null hypothesis. So I'm going to fail to reject the null hypothesis. So here we go. My p-value is above alpha. So I will fail to reject the null hypothesis. Okay, really good sentence, me, but I have said nothing about battery lifespan. Exactly, about batteries. So how can I make this about batteries? What am I saying about this company and their batteries? Evidence.
You claim that the battery lifespan is greater than 3.
Perfect, okay? So at this point, I do not have enough evidence to claim that Batco's batteries last on average longer than 5 hours. Now, I just said a lot more words than I really needed to there, but ultimately what we're saying is we're going back to this. Let's say we were a company hired by Batco, all right, to do the testing. So we're going back, giving our report. You know what? Based on what you gave us, we don't have enough evidence to say that you can claim that your batteries last longer on average than 5 hours. And they say, okay, fine, we'll pay you more money, do it again with a larger sample. Well, then I'd be more confident in our conclusion. Okay? And then if we come back again, like, all right, you got to change your batteries. It's not working. All right, who's got questions? Can I show you guys what? Yes, Kiara, question. Oh, I use MathCracker. So I use the link to type all the stuff in, and it gives me the p-value, which is right here, p-value. Okay, another way to do it, let me show this other way. I included this in the link. Did you guys, none of you probably opened the link because I get it. But like, this is a link here, all right? You see our degrees of freedom is 11. What was our t value? 0.738. 0.739. I rounded it, okay. And then if you hit enter, should hit enter. Can I hit enter?
I think it's the red one.
There you go. Just had to hit enter. Enter. And you see how the p-value is 0.238. So you can also do it this way. And there's our curve. Now watch this, all right? Because you guys didn't believe me that it looked different. You ready? Okay. Ignore the shading. Just watch the curve. Okay, everybody watching the curve? Watch the curve. Not me, the curve. Watch the curve, okay? What if the curve, what if I had used 100 batteries? Right? You see how it changed? It's not the same though, right? It is different because now watch where my 0.79 is. 739? 739. And you see what happened to the p-value? I mean, I know it didn't change much, but it changed. What if I had only had 5 batteries? Ready? Look at that p-value. Changed again. So what I'm trying to say is that it's not like the normal model, which is the same every time. It changes based on your sample size, which drives your degrees of freedom. All right, the larger it is, the more normal it looks. Watch the degrees of freedom of 3. It's a sample size of 4. You see that? That was much more narrow, but watch when I do a 300. It's wider. What, Guillermo? How many 9s? See how like 300 to 99.99 didn't really change much at all. Right? Once you kind of get really big, it doesn't really change much. All right, that's when. So what? This is the crazy part. I'm going to stop the recording because this is not important. Cool.